or how you struggle to remove them. Okay. Hi, everyone. So my name is Faustine, and I'm currently working in France, in Grenoble. Um, I just wanted to show you that because we found that quite interesting with some colleagues. Yeah, Kim, we talked about it before. So exactly 10 years ago, I was here sitting here as a first, second year PhD students. And here I am giving you a review talk. So I hope that sends you some good vibes and lifting you up. Everything is on YouTube. That was me 10 years back. I think my slides are much better now, but anyway. So I'm still doing the same stuff actually. So it's post-processing for high contrast imaging. And compared to what we had this morning, I'm going to mainly talk about ground-based telescopes. You've heard that before at Best Talk, but just a quick reminder, what we call direct imaging today evolved a lot. So there is, of course, high contrast imaging. We've had a lot yesterday morning, but also high contrast imaging, low resolution spectroscopy, so integral field spectrographs. We also have like high resolution spectroscopy with or without coronagraphs, like Symphony, for instance, ISO, VLT. High dispersion coronagraphy is like K-peak, high-res, rich. So where you put a fiber on top of the planets and then send it to a very high resolution spectroscopy instruments. The last one is the sparse aperture masking that you also touched upon yesterday, and we're going to have a talk by Steph Saloum soon about it. Same for the HRS. We're going to have a talk by JB Rufio as well during the week. And the very last one, which we also will have a talk about within the week, it's long baseline interferometry, such as the exogravity program. So I'm going to focus on the first two ones. So in any case, for all of those techniques, we are looking for faint objects at very close separation. So faint objects, we need a higher sensitivity. So the biggest telescope, the better, because it scales with the diameter of the telescope. So you collect as much light as possible, close separation. So you also want to have an extremely large telescope, no puns intended. So to have a very high angular resolution that we talked about yesterday as well, and close to the very bright host star. So you want to reach a very high dynamic between the star and the planet around. So using, for instance, coronagraph, but not only. So I'm going to mainly focus on ground-based telescope from the A-meter class, because that's most of the things we have nowadays in the near and thermal infrared, so H-band to N-band, and focus on those two techniques here because you're going to have dedicated talks to about the others. So high contrast imaging is like, again, we want to reach a few milliarcsecond angular resolution and contrast more than 10 to the minus 6. We want more, obviously, but that's what we have. We are looking at emitted light from the giant gaseous planets with these techniques. So sometimes this high contrast imaging is the so-called coronographic imaging. So here I'll put like lots of vocabulary so that in papers, there is like different vocabulary used. You can like find your bearings. So as I said, first, you want to have a big telescope, so 8-meter class and plus. And if you look at a star with ground-based telescope, that's the fuzzy thing you're going to find, you're going to have. So that's why we want to use adaptive optic system. We're going to hear a lot about it today as well, to recover the diffraction power of your telescope. So here in this image, almost 90% of this is corrected, which is great. So it means like 90% of the light is like not spread over outside the core of the diffraction area ring that you've heard a lot about yesterday. But this is not enough because here you see objects like only 1,000 times fainter than the star. So we add a coronagraph. So here is the example of a focal plane mass type of coronagraph. So low apodized coronagraph that we've seen yesterday. But it's still not enough because the contrast you can reach here, you can see objects that are 10,000 fainter than the star. And we want 1 million. So that's where the post-processing step is absolutely important to gain those 2 orders of magnitude and carve out the starlight to get those planets. So here, we go from the 2 last hand side. We call them bright starlight residual. Sometimes we call them stellar halo, which is nice, but it makes us think about something fuzzy, so it's probably not the best, or speckled field, which is nice, but then you forget about the fuzzy thing, which is still there. Or one vocabulary we liked with Jason Wang, who's been preparing that vocabulary list with me, is the stellar glare, because all of the things you see here is actually the light from the star that is spread around in the field. Very rarely you will see the planets anywhere here. So the important thing, why do they come from? So, I mean, we already saw that is the incoming ray front is obviously not perfectly flat. There's lots of like aberrations. We saw that yesterday. And it's just like interfering in the focal plane and having those bright speckles. And because of this interference pattern, all of the speckles are the size of the diffraction objects. So the same angular size as planets, lambda over d type of, exactly lambda over d Liu. But we saw that yesterday. Okay, and between adaptive optics and chronography image that I'm showing you here, there's a so-called pre-processing step, sometimes called calibration or cosmetic or like data pre-processing. This is just like to remove bad pixel, flat fielding, dark field. So I just wanted to mention that I'm always going to talk about once it's done, like once you have just like the clean chronographic images. So there are 4 big things that are actually preventing from having a perfect image post-processing. So there's lots of adaptive optics residuals. The adaptive optics is not perfect. There's low order aberrations. So due to, for instance, vibration, jitters, something called low wind effect that we're going to hear about in Julian's talk. Actually, Julian Milli's talk on Thursday is going to talk about all those things way better. We also have the so-called non-common path aberrations, aberrations seen or not seen by the AO, but seen or not seen by the science path. And of course, all of the detector noise. So if we want to summarize, we have this somehow clean chronographic image here. Yeah, no worries. Thank you. Oops. Yeah, then we have to click on it. Yeah. And what we want to do is first have the detection. So we want to discriminate between the null hypothesis, there is no companion, and the what H1 hypothesis, which is we have a companion with a certain confidence level, obviously. Like we know it with like a probability of X%. The second thing is the characterization. When we say characterization, what we can have with a 2D image is the position, the astrometry, and the photometry, if we have several wavelengths, is spectrophotometry. And the same, always give it with uncertainties. There's also another thing that's quite interesting is the detection algorithm, which really gives the how the algorithm can dig into the data to find planets. But also if you want to compare if you use different algorithms, you want to compare them. So there's like more algo-centered comparison. But the ultimate goal is to maximize with your algorithm the true positives. And it's very obvious what I'm saying, minimize the false negatives. So this works for point sources, so any substellar companions, but also for extended sources, so any type of circumstellar disk. Yeah, so that's the thing. That's what we want to do. You ready? Because that's going to be long. So yeah, don't forget like this talk by Julien to explain. Okay, so 101, differential imaging. That's what you've probably heard many times before. So what's the baseline today is that we have a 1 hour observation temporal cube of chronographic images. And we have to find a different behavior between the starlight residuals, the stellar glare, and the astrophysics signal, so disk or planets that we're looking for. And we want to exploit this so-called diversity to recover the signal. So the basic steps are 1, we have to estimate the image of the star alone without any planets or disk inside. Sometimes we call this reference PSF, and that's how I'm going to call it for the rest of the talks. Then you subtract it to the image, and then you combine all of the subtracted image of your temporal cube out there. And doing that, you start to see HR 8799, but it's not enough because usually you want to build a detection map, something that tells you, okay, above the threshold, here it's just one threshold. This is very likely companions, and below the threshold is likely to be noise. So yeah, that's an example of like detection by thresholding. You can optimize the combination of image. This is a very important step because it whitens the residual, and it's under the assumption that all of these starlight residuals, they are not moving that much. They are correlated in time. So if they are correlated in time and that you do this subtraction, then you whitens the residual, which just means like with simple words, you decorrelate them because they're correlated. So it's just, okay. And this step is absolutely critical because if you do not estimate the reference PSF the right way, you will have more and more residuals here. And the variation mainly come from, as we saw yesterday during the several talks, from the very close to the star, which is exactly where we're trying to find planets. So it's a bit annoying. So for that, you need a very specific observing strategy and calibration procedure, and you can have various diversities. So it's a non-exhaustive list of the thing that exists in the literature. So you have binary differential imaging, reference differential imaging, multi-reference differential, polar imaging, all those things, okay? It's a lot of differential imaging. They all work on the same concept, except that the diversity is different. I'm going to focus on the angular differential imaging because that's how most of the observations are run today, but there's like lots of interesting things as well, obviously. But so angular differential imaging works when you have an altazimuthal type of telescope. So here is the Subaru telescope sketch. With this altazimuth, you have two options. You can put the field tracking mode and like fully follow your object, or the pupil tracking mode, which is exactly what we're going to do. The pupil tracking mode is this one. So this is the observing time here, and you follow your object in the sky. And the pupil that we saw yesterday, so it's very good, does not move, which means the stellar light residual pattern, the diffraction patterns of the stellar light does not move, which is what you see here. So this is the pupil, but this is the image plane here. So you see it's very fixed. But the planet that you're looking for, because the Earth is rotating, you all know that. So it's going to move with time. And you know that if a planet is here at this time, then at the end of the session, it's got the observing sequence is going to be here. So it's a deterministic way of having the position. All right? Because it's all based on this. Okay, so this brings angular diversity, as I said, and again, it's a technique. It's not an observing mode or data type, but often in papers, you will have an ADI data set, which formally doesn't mean anything, but it's fine. Okay, so the very, very, very basic approach, as I said, because of this temporal correlation we have between the frames, is to do a pairwise subtraction. So you take the closest frame in times because they're still correlated, but you don't want to take them too close in time so that you don't self-subtract the planetary companions if there is one. So for instance, if you take the first frame here of a random image sequence from the sphere instrument here, and you remove the second one, you see that you do have a lot of residuals, but it's still better than the first one. So that's the very, very basic thing. And it turns out the optimal angular movement that you want for your planet companion is 0.5 lambda over d. Oops. But this depends on the distance to the star as well. So yeah, that's one first thing. The second one is the most famous one, and is the very basic one, is to use the temporal median. You know that the temporal median of your cube should represent the stellar glare across time without accounting for the moving signal inside. That's the concept of the median. So you have the temporal median of the same cube here. It looks like that. So you see it's very similar. You do the subtraction for all of the frames. So all of the frame of your cube, you subtract the temporal median. And at the end, when you derotate and combine your frames, that's what you obtain. So it's not perfect, but you see the stuff inside, which is pretty cool. That's the thing we're going to do this afternoon during the hands-on session led by Jason. So this ADI thing so it's the classical ADI method, the median. It comes in many flavors. You have the so-called smart ADI that takes into account the fact that depending on the separation of your companion, it's different. You have the annular ADI, you have like lots of stuff. Blah. Then there's another classic approach that I think we're going to do as well this afternoon, which is the principal component analysis. You're like, yeah, sure. But if you do a SVD, a singular value decomposition of your image cube, then the first PC principal components, should represent exactly how the biggest contributions to your stellar halo, your stellar glare. So this has been published here, and this is the first principal components. It's very similar to the median, temporal median. This is the second. You see there is like structures popping up, and so on and so on. And this is the last one, which is extremely noisy. So if you cut here and you say the sum, so the linear combination of those first species is my reference PSF, then you can subtract that to each frame of the image, then derotate and combine, and then you have a much better subtraction than just using the temporal median as I showed before. So there's lots of flavor. There's like LLGS, which is like robust PCA kind of. Recently MAT, which uses also the temporal and not only the spatial correlation. There is non-negative matrix factorization, sorry, a lot of stuff, and space-time clip. So a lot of literature. But the concept is this, and then there's many ways of doing a better PCA that works better. And another very famous one that you will probably hear when reading literature is called LOCI, for locally optimized combination of images. So it finds the linear combination of images that minimizes the residuals. So it writes like this. It's disgusting, but wait, there's a minimization the residuals here, the standard deviation of it. This is the stellar reference here. So it's a linear combination of a subset of images. And that's the image that you're looking at. So you want to minimize to the square this term here. Same. There is lots of flavors: template low-key, adaptive low-key, match low-key, damped low-key. Lots of fun to change this equation here, like slightly, but concept is the same. You take a linear combination of the subset of image and you minimize the residuals between the frame you're interested in and the model, the PSF reference. I wanted to say one thing about it. I forgot. Yeah, okay, I'll tell you later. There is another technique that's been recently like put in place. It's a causal method. So it says like here, no, here. Yeah. Yeah, so that you do, it's very strange. I'm going to do it by hand. I'm sorry, I'm very old fashioned. So you do have a relationship between the noise you observe when it's like the case of planet plus noise and only the noise. And you can use that direct causality by using the noise to predict the noise here and get the, it's exactly the same concept. But so like in this thing, so he really predicted the systematic noise in a different way. So he used like a patch that is opposite. So considering one pixel here, like you exclude the pixels around because it's too close, but you use the blue zones to actually assess the systematic noise. And another one that Marcus Bons is here. So anywhere I put the picture of the people, it means that they're here attending the second summer workshop. So please go to see them and talk to them if you want more details. So it came like recently with a 4S signal safe spectral subtraction. So using machine learning and similar principles. So it's like a PC as well, but like digging into like why it's not perfect in terms of like self-subtraction mainly. So the first PC principal components actually have a bit of the planetary signal within it. So how to get out of that. But one result that is important, so he used force to rerun the very old NACO data in the archive, and he found AFLFB in those images. And it's great because compared to it was like years before in 2011, so you have a long timeline. The conclusion of that is that it's quite important actually to work on better algorithm and to understand better what's going on in the data, because then you can revisit archive data and find some very interesting scientific astronomic results. Okay, so one very important point is you still okay? I haven't lost you, right? Okay, yeah, some people are laughing, it's fine. Thank you very much for still being here. So one important thing in, the step number 2, which is slightly hidden here. So when you do the subtraction, there's many things that you have a hypothesis of like how the noise distribution behaves. And it turns out that one of the things in this so-called subtraction residuals or differential image or residuals or post-processing residuals, so the residuals after the subtraction, may be PCA, low-key, or whatever, we always kind of assume that it's Gaussian, but it's actually not Gaussian. And that explains why we have a lot of false positives. So signals that pop up above a threshold that are actually just noise. And which also means that when people are like computing the performance of the algorithm, they're over optimistic. So we tend to think we have a better discovery space that we actually have. And I think that's important to keep in mind. I don't know if some of you are into math, but you probably saw that everything relies on a least square minimization. So it reminds you of Gaussian distribution, and that's where it pops up as being wrong. So this is a disgusting image showing like if you take this residual map here and like you just move the threshold here, so it's just like it's equivalent threshold, it's exactly a threshold. You see that first it's like really like showing less and less pixels, and the higher the threshold, you have like very low pixels above this threshold. But these two trends are like very specific. And if you take before the subtraction, you take like some pixels and you plot the QQ plot. Okay, the QQ plot is something really funny. It's quantile plots. If the noise was Gaussian, those points here, which is the data, would align perfectly, kind of perfectly on the orange curve. Okay, so that's before. And after the subtraction, you see that same thing. It should align with the orange line here, but it's not perfect. And it's not perfect because the noise is not Gaussian. Again, so it depends on the data, on the instrument, of the observing conditions, and on the distance to the star as well. But I just wanted to point out that because I think that's very important to keep in mind and to realize the number of false positives is higher and what we're saying. So one way to fix that was to rethink the way we actually compute the signal to noise ratio of a detection and the confidence level with it. And so and so the detection limit. So I'm not going to go into details, but again, Marcus is in the room and he can explain you that much better. And there are 2 papers that are actually deep diving into this concept. Right. Yeah. And that's the kind of conclusion to really point out on confidence level. Another stuff is how to combine the images. Usually we do either a mean combination or median combination of the images once they're subtracted, but there's no formal proof that one is better over the other. And that's something you can check yourself next end-on session. So there are so many other ways to do it. There is like noise-weighted combination of those subtracted images. There's the STEAM map, which is like you weighted by the standard deviation along a temporal axis there. So normalization factors kind of to optimize the SNR at the end. There's also the statistical testing that takes into account the small sample statistic, which means close to the star, you have very low pixel and very small rotation of the field of view. And same, you can have like empirical normalization, which is like, this should be straight and it's not straight, so let's make it straight. Which is, yeah. Okay. I mean, it works. So, and there's also like even more like statistical testing of that, such as the multi-nest approach and the SNAP approach that recently got online. So, and it's just to balance the noise reduction versus like how intense is your detection. Okay, so there's lots of literature. One other thing, which is funny about this combining the residual images, so is the slim mask is to say, okay, then I'm going to take the best SNR maps I have and just combine them after, for instance, the PCA subtraction. So I'll do several times the PCA subtraction with different number of components, take the best and make a mask, like correlate them. And yeah, it kind of, it's very simple and same, it works. Simple works. There is a bit more evolved, so to say, I do a way of saying that by Karl-Henrik. It's actually taking the residuals after both Loki, PCA, NMF, and so on, even pairwise subtraction and everything. And that's something you can talk with Mariam, who is also attending the Sagan workshop, because she's working on that. But it's another way of seeing the problem. Now, fourth step is the detection map. So usually we do it by eye. We just say, oh yeah, it's above the threshold. Yeah, we have a planet. But there are some ways of so Sodin's been developed to make a binary classifier between we detected something, we did not detect something. So yeah, it's just using the noise class versus the signal class, and it's within a CNN convolutional neural network framework. And there's a new one that appeared, which is an adaptation of that, which is called noise adaptative Sodin. Which uses on top of that the curves, the SNR of each pixel or like element of resolution as a function of principal components that you're using. And Carles, I think should be here, but he's actually not here. No, he's not here. Okay, Mariam is telling me he's not here. But yeah, shame. I thought it was here. It was on the list. Anyway, so yeah, Carles, sorry, is not Carlos and Carles, different thing, is working in Geneva right now and works on that. Okay, so now we have our detection. Next step is the characterization. There's 2 ways of doing it. Either you do it here by injecting, for instance, negative fake planets in your data and try to minimize the residuals to 0. So that's kind of what we're going to do, I think, in the end session. That's a very usual way of doing it. There's another way here, is to do forward modeling. You know that if you have a signal somewhere, you can make a model of it and then track it into the images. But this relies on a very strong assumption on the noise distribution, which is not Gaussian, I told you, right? And then by construction, this forward modeling method actually gives you a direct SNR estimate by just saying that it's the estimated flux over the uncertainties on your estimated flux, SNR. So the basic concept of forward modeling, because I think it's quite cool. It's also sometimes called inverse problem approach or match filtering approach. So the basic concept, so I took the example of like Andromeda, but they're all like the same thing. So you do a subtraction and you obtain the first differential image or residual image, blah, blah, blah. 2 things. If you have noise, null hypothesis, then you assume it's white, decorrelated, and Gaussian, which is wrong, but it's okay for now. If you have a planet, then you just subtracted 2 images in time, so you have the blob negative and positive blob, okay? And you're going to track that in the image. And funnily enough, if you do maximum likelihood of that, so this is the model here, the data here, minus the model. So it's a factor of flux and the planetary signal, which is like negative, positive blobs. And you can actually have an analytical solution because here you have the square because you assume the noise is Gaussian. Perfect, easy peasy. It's not perfect. So why not doing a better subtraction? So it's a bit the concept of like for one modeling match filtering, which is hidden, unfortunately. But you do the subtraction instead of pairwise subtraction. This time you do a linear combination of the first principal components. And better white and Gaussian, hopefully, but still like the same model here. But if you have just a positive bump. Same analytical solutions, it's long to compute because you have to run lots of PCA. So it's like, okay, so that's one thing. You do better subtraction. Another thing is we stay with the pairwise subtraction, but this time we do a better noise model. So instead of saying it's Gaussian, let's say it's Laplacian, which is way more likely to be the case. So we did that, and then the same as before, except that if you have a L1 norm here, so the square disappears, there is no analytical solution. So you have to find a numerical solution. Just wanted to point out that I submitted that paper in 2019 and I still haven't resubmitted it. It happens. I'm fine. And the best thing you can do is like, okay, let's even avoid the subtraction and take into account the noise for what it is actually. So the model of the planetary signal is just the positive bump, and the model of the background, well, that's complicated. But Olivier Flasser in PACO, for patch covariance, he's actually doing a maximum likelihood estimation on a multivariate Gaussian noise. So instead of taking the sum I showed before, it's like the product of like lots of Gaussian layers, right? And he estimates this on like patches following the time thing. That's the best you can do, I think, at this stage for one modeling. There's also like another way of seeing that is like, it's very similar actually, but it's like taking patches in these white areas here. So if the planet is here in the middle, yep, too small. In this white area here, you find the other things, then you do a decomposition, a PCA, but within the time direction and blah, 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 and you fit the thing. So there's no other very similar technique, but slightly different, but also assuming Gaussian. Right. My favorite side. Okay, now, just a summary of what I said. You have lots of things, let's get idea, low-key PCA, idea, lots of things, like really lots of things. It's the same slide as yesterday David showed us, like lots of things. Like really, this guy published a lot, this guy as well. You see, but my favorite is this one. Don't copy that, only professional can do that. Okay, so what do we do with all those things? Like, it's super hard to compare and to say, like, you know, people working observation, oh, you should use that. So that's how the Exoplanet Imaging Data Challenge took place. So it's really a community effort. There's lots of people. So sorry, Carlos is not here, but again, Marcus, JB, Sandrine, Julia as well. We are here this week. And so we started this data challenge. So it started in 2019. We had like first phases, a workshop dedicated, first publication. Now it's the second phase, which is dedicated to characterization. The first one was dedicated to detection, the first step. And later we want to do disk imaging contest. So if you're interested, it's a community-wide effort, a volunteer-based. So if you want to join, please let me know. I'd be very happy to include you in the team. It's very fun. Like really, we have nice meetings. So we used mainly data from Gemini, SAS, GPI, from Sphere, IFS, and IRDIS, Keck, NIRC2, and LMRCAM. You have the website here. There's a lot of bibliography on it, like information about the data. You can use the data for your own fun if you want to play with it and so on. There's lots of things you can find in literature and bibliography. So, and I'm probably going to put that presentation and our video on it, actually. That would be a good idea. So link to a website. So there is also the data repository, which is Zenodo. So it stores the curated data set. There is the competition platform. So we used EvalAI before we used CodaLab. So you can submit your results there. And then there's tons of resources on GitHub with like tutorials for metrics and everything. So you can have fun with that. Now, what do we do today? Usually in papers, either we have like image comparison. Oh, this one looks better than the one on top. Or you can do a detection limit comparison, the so-called 5 sigma contrast curves, and say, oh, my curve is actually better, like below the one on top, so better. Or you can do the ROC curve, the receiver operating, oh, the C is missing characteristics. It means characteristic curves. And usually if you have, it's a number of false detection as a function of true positive rate, a perfect algorithm would be like phew, 1 and phew, straight ahead. So this one is pretty good. It's supposed to be Paco. And the other ones are just like, it's kind of a way of assessing. So in the literature so far, before the data challenge, that's what we had. And so we asked the participants to data challenge to give a detection map, a given threshold, and a posterior note at all. Just the detection map and the threshold. Sorry about that. Miss copy and paste. I'm a human too. Okay, and then we counted the true positive and the false positives and the true negatives and the false negative. So we had a set of ranking. I'm not going to go through that. There is a paper about it, but I just wanted to show you the different maps here. So you see encircled in yellow are the true positives, and in red, there's no red here, the false positive. So it's good actually, but it's nice to see like all of this gallery of images. So you'll find everything in the paper. And then based on those metrics, we had like the ranking with different types of scores. So it's one example here of who does better. It seems that FMMF, no advertisement here, is doing amazing. Keep it for yourself. Anyway, and the second phase of the challenge, as I said, is the characterization. So we injected in multispectral data, we injected planets with a given at given positions that you see on the left and with given spectra, as you see on the right. So one is like just straight spectra and the other one is like a T-type spectra with like 2 bumps. And we asked the participants to send us the astrometry estimate and the uncertainties, and if they wanted to, the posterior distribution. Otherwise, we assume that it's Gaussian. Okay, so the astrometry looks like that. So for instance, here you have the detection limit with Andromeda with like a very basic PCA. And on the left here, you have the ground truth in the middle, and the closer, the better. So you see that Andromeda is quite off for the first planet, but it's actually getting better when the planet is further out from the star. So Andromeda is the blue one, which is normal, kind of expected. But NegFC is actually doing really good with the PCA to have that. And that's the same thing for the spectrum. Yeah, Andromeda is a bit awkward here at longer wavelengths, but here both of them match really well. And so your extraction is quite consistent. Okay. And you have the ranking, so everything is on the website. Again, I think you need those breaks as much as I need it. Or maybe I need it more, I don't know. I love penguins, by the way. Another topic is the circumstellar disk. So we heard about it this morning. There's like lots of extended structures. So it's an example of one gallery that has been made. You see gaps, you see rings, you see all like structures, spirals, shadows, dips, whatever. And also you want to disentangle the planet signal from the disk signal in which it's often buried. So that's what we want to do for the phase 3. So the classical approach are the following. So the first one is to really enforce, like to mask the part where the disk is and like iterate on it and enforce this positivity. So you can find some papers here. We know if you have like a model of a disk on the top here, it's just a model, like a radiative transfer model of a debris disk, and you apply a basic ADI with some assumption, that's the distortion you're gonna have. So basically everything here is going to be subtracted and everything here is going to be subtracted, which makes sense, right? So if you have a perfectly edge-on system disk, then with the rotation, it doesn't change. So you have barely any self-subtraction. But if you have a perfectly circular centered face on disk, you have no diversity at all. So whatever you do, your signal is disappearing, your disk image, right? So in between those two limits, there's stuff you can do about. And another way is to do the classical PCA again. So this is ADI, but you see those like artifacts here and on the edges. So what you can do is again to mask and to do like iterative PCA to make sure that you remove in your reference PSF any signal from the disk. And at the end you have that. And this image was really cool because they were kind of fighting to know which one was the forward scattering thing. So talk we heard about this morning with John. So they were like, oh, no, it's here, no, it's here, no, it's here. And then you have this image like, eh, it's here. Okay. But there are like more fancy stuff. So one thing is the mayonnaise algorithm. We got lots of good feedbacks about the name. So really, people got crazy about it on Twitter. I'm not on Twitter anymore, which is good. So it's based on a morphological component analysis, which means that you consider two space, one space with the disk that we described here in the linear combination of shearlets. So it's a bit like Fourier transform, but a bit different. And the planet is a point, so we decided to work on it in space. So you can see planet B and planet C. But Mustard does much better. So Sandrine is here attending the workshop, and she actually took the problem from the roots and did everything much better. And so like masking the thing here. So yes, similar type of image at the end, but the better, like, I mean, it's nice to have like several algorithms, so it's more reliable. And the last one is PACO, Rex PACO. So it's the PACO concept I showed you just before with the 4-1 modeling, integrating the disk inside. And the cool thing about those images, the three of them, they were the first ADI only based images of the intensity of debris disk. And they show the same features, the planet B, the planet C, some weird stuff around, the spirals here that Sandrine has been actually characterizing and so on. So it's pretty resembling. One take-home message, use as many algorithms as needed because we never know what's happening. But those three are quite different on similar concept, image reconstruction. So yeah, it's better. And to go further than those disk algorithms, like just in general, as I told you, a critical thing is to build the reference PSF. So you can use multi-reference differential imaging. So by using a library of lots of images as a database, and then there's different ways of actually saying, oh, those images are good for making my reference. This one is to be discarded. So there is data imputation, there's structure similarity index. This one looks really good, so let's take it. Or even autoencoders based, so AI-based techniques. And again, there's a poster by Sandrine. I couldn't find the picture of the person. So I saw there is like a data imputation with CNN poster, and Sandrine is combining ADI and RDI for better results. There's also observing strategies. So for instance, using another star of reference. And I just wanted to point out those two methods because I think they're pretty cool. So the first one is like to take a snapshot of like stars that are very similar and with similar observing conditions and just like take many of them and then use that as a reference PSF, hoping that most of them don't have planets. And turns out that they found a lot, so it's pretty good. There's also two posters about the YSS results, which is the YSS is the first technique. And the second one is a star hopping observation, which is a specific mode at least offered with the sphere instrument at the VLT, which is like going back and forth very quick on the reference. So you hope that you have the same stellar glare structures. And a last thing I wanted to talk about, let's maybe even estimate it with an instrumental model. And that's the work that Rodrigo has been starting with Jason Wong. So he's here and he also has a poster already. And the idea was like to say, okay, so apply to JWST, but I think the concept works after for anything like we know the perturbation, the aberrations we have in the telescope, so we can reconstruct the chronograph image. And then we can use that as a reference model, which I think is hopefully it's going to work out. Good luck, Rodrigo. I hope it's going to work. Okay, last word about the pipelines. So there's lots of things that are available. There is the Pikely pipeline that you're all going to use this afternoon if you come to the hands-on session, mainly developed by Jason and collaborators. There's lots of stuff inside. There's the VIP pipeline with also tutorials that so quite well used in the and pinpoints. So all of those pipelines are available. They're like lots of other tools, but those three ones are very complete and they can be used for different tasks. So feel free to go there, talk to the people, give feedbacks as well. We love feedback in the community. Please tell us if you're not happy with something, we're going to change it. So yeah, you can use that very easily. So summary, key points. So post-processing is more than essential to gain one magnitude, at least. Understanding the limitation of high contrast imaging is actually very important. And one takeaway with the methods we have to stability. Temporal stability is a huge important stuff. If you build an instrument, make it stable, please. It relies on specific observing strategies and calibration. Characterizing the starlight residuals is also very important. As I told you, forget about the Gaussianity, more false positives. So what my take is that there's lots of algorithms. Use as many as you want, but use several of them. Never use only one being like, yeah, this is the king of the algorithm. It doesn't exist. They're all different performance compared to like different instruments and observing conditions. And yeah, so it's no views, data challenge, great. They're available. There's little, so what I said, and penguins. Okay, thank you very much.
Cool. We have time for a few questions. Okay, so still over here.
Hi, so thank you for your presentation. I'm Fang from UC Riverside. I'm also the author with the poster 8. So I'm currently working on this issue with Renbin. So I'm kind of have a question about the classification problem. So most of the pre-existing detecting result is kind of still labor dependent. So it's you talk about statistical testing and to PCA and math, and then more deep learning based algorithm. But for a current new trend is more machine learning and deep learning based, but those kind of trend has a significant shortages that is very data based, and we don't have enough data for labor data for training those models. And the same for the imputation problem, like the reconstruction of the image. We still need a variety of label data for training. So what ideas would you give for addressing this issue?
Yeah, no, it's a very good point. So we start to have a massive database where we can start, learning a lot about those things, very highly dependent observing conditions, which is absolutely random for some surveys. But we often use data augmentation, and that's something I didn't point out here. But there is, for instance, a way of mimicking that the parallactic angle is actually the inverse, so that you kind of keep the same temporal correlation, but you lie about the direction of what happens. So that's a way of doing data augmentation, or by injecting things, or by doing the simulations as Rodrigo is doing something similar. So there's ways, it's I think it's the beginning of the AI-based era. So that's also something we can talk about with Marcus, because he's kind of reviewing. Actually, I wanted to thank Marcus for helping me putting the stuff together and finding a good line for a good storyline. Because it's the beginning of the era. So we're starting, and you see the first paper Sodin was in 2017. It was really the first one. And then it was very difficult actually to get the Lil Nox to make it work, because the data challenge results on this 2017 paper are actually not great. There's lots of false positives. So, it's but yeah, happy to talk about the different
Sure.
things with you.
Yeah, we want to have one or two more quick questions.
Thanks so much. So I have a quick question about the forward modeling approach, with the caveat that I don't know much about this, so I might have just misunderstood. I was wondering why you have to assume, say, white noise or Lorentzian noise, instead of just directly calculating the noise PSD and using that.
Yeah. So you don't have enough pixels to do, for instance, this kernel fitting of the actual PSD of the noise. So you do have to make an assumption on that.
Okay.
That's one of the major issue, and that's what Paco is trying to go through by doing this multivariate Gaussian noise. But so it's super important, because your fitting, which is the distance between your model and your data, how you judge that distance, so L1 norm, L2 norm, whatever, is dependent upon the assumption you make on the residual noise. Does it make sense?
Yeah, it does.
Yeah. Okay. So, but it's actually indeed we thought about this kernel fitting, for instance, to say, okay, we have noise, let's fit a probability density function, but it's not enough pixels and data.
Okay, thanks so much.
And varying a lot in time. The types of residuals we have in the pornographic images are really different. Some actually move with the parallactic angle, such as the wind-driven halo. We're going to talk about that later. You touched upon it yesterday. So the types of aberrations we have are actually messing up with all those assumptions as well.
If you had faster time resolution images, would that help, or would there still be not enough signal?
That's a good question. And actually, that's what also Marcus kind of worked on with his 4S paper. And he kind of proved that, yes, it does help somehow. But yeah, that's most of the instrument deliver. I mean, you need sensitivity as well.
Yeah.
So if you're in the thermal infrared, it's good to have lots of frames. But if you were H-band, then faint star, you need at least 1 second or even 1 minute of data. If you do spectroscopy, it's even worse.
Okay. So, that's really interesting. Thanks so much.
Thank you.
All right. We have one more super quick question.
So thanks for the interesting talk. You mentioned the high amount of false positives, and also number of different methods for the post-processing. Are there any like rules of thumb where you like look at your own images or like reported point like sources or anything where you go, oh, I trust that, I don't trust that? Or is it
No.
no? Good to know.
Is that a good answer? No, I mean, no.
And that was a super quick answer.
Made my best.
All right, awesome. Can we thank Faustine one more time?